variables. Okay, so now we have this conceptual model, this diffusive time constant that we can use. Let's actually go through how to solve the problems analytically. Okay. So this is the same kind of approach that we've used before for separation of variables, but now what we're going to do is we're going to separate variables for one coordinate of position and one coordinate of time. Right, and that difference actually changes the approach that you're using a little bit. So let's do the same thing we've been doing. We have this current lead. We have, okay, we call it X. Sorry for getting that to R, but we have X as our coordinate, and we have time as our time component. We're taking it and switching it off at the initial condition. Okay, so let's go through how to solve this with separation of variables. So here we had our initial condition, right? This function is our initial condition at time equals 0. This is from the solution for the initial steady state temperature, right? Before we make this change. So let's go through and do an energy balance on this. So we're going to pick some point. Let's draw out our wall here. Okay, and we're going to do a control volume and do an energy balance, same as we've always done. So this is now coming in. We have Q dot as a function of X, or Q dot at position X, and we have Q dot at X plus dx. This width here is dx. In here now we have du. Sorry, be careful. It's a partial u with respect to time. Okay. And then that's it, right? We don't have any generation going on. So then we bring this together for our energy balance, and we have Q dot at X is equal to Q dot at X plus dx plus the partial of u with respect to time. Okay, expand this out. I'll just go through this quickly because we've done this a million times now. But expand it out and you end up with 0 is equal to the partial of Q at X with respect to X times dx. Plus the partial of u with respect to time. Okay, just skipped one step there, but that's what we end up with. So now we need rate equations. So our rate equation for conduction is Q dot X is equal to minus K AC, partial temperature with respect to X. And our energy term, our stored energy term is the following. It's rho times C times volume, which is AC times dx, times the temperature derivative with respect to time. Okay, bring that back together, and we end up with 0 is equal to the partial minus K AC TDX, X, okay, times dx is equal to, sorry, plus rho C AC dx dt dt. Okay. Okay, one more step then to simplify this down. And let's introduce our thermal diffusivity, right? K over rho C, which is alpha. And this actually simplifies down to the following. Alpha times second derivative of temperature with respect to position is equal to the first derivative of temperature with respect to time. Okay. So yeah, we've gone through now. This is our energy balance and our governing differential equation, but note how it's different, right? I mean, it's kind of obvious. Now we have, before we had the second derivative of temperature with respect to position X and position Y in two different terms. Now we have the temperature derivative is equal to some time derivative. Okay, so that's kind of the key difference here. Okay, so let's go through and check for separation of variables requirements now. So the same separation of variables requirements apply. The PD and boundary conditions must be linear. The domain must be simple. The PD must be homogeneous. And both boundary conditions in one direction must be homogeneous. So is the PDE and the boundary conditions linear? Yes, you don't see any products of multiple variables there. The domain is simple, right? It's simple in time, it's simple in space, and then the PDE is homogeneous, right? You don't see any leftover stuff in the PDE that's kind of unrelated to the derivatives. both boundary conditions in one direction must be homogeneous. So we'll get to that. Let's actually write out the boundary conditions here. So we have our initial condition, right? Let's write out the boundary conditions. The boundary condition at 0 is the partial with respect to x. At x equals 0 is equal to 0, right? It's adiabatic. Okay, and the other one is conduction has to equal convection. So we have, right, let's do this carefully. So we have a surface balance here. Surface balance is infinitely thin. So we have heat flowing this way, heat flowing this way. So if I match my arrow direction here, we have conduction, which is minus k times the partial with respect to x at x equals L is equal to h bar s t at x equals L minus t infinity, right? Those are our two boundary conditions. Okay. Good. So let's go through and solve this. Okay. So here's our statement of the problem. If you note though, we don't have a homogeneous boundary condition or boundary conditions in either case. Let's look back here. We have for time, right? It's not homogeneous in time because there's stuff in that equation that is not multiplying time or its derivatives. And the second boundary condition is not homogeneous because T infinity appears as well. Okay, but we can deal with this pretty simply if we just say that theta is equal to T minus T infinity. Right? You can make that substitution. So let's do that. So first substituting in here, right, this equation here, we end up with alpha times the second derivative with respect to x of theta is equal to the first derivative with respect to time. Okay, then this equation here becomes theta times, or theta at t equals 0. So we said t minus t infinity is theta. So now actually on the right-hand side, t infinity goes away. And we're left with just is equal to g dot triple prime over 2k times x squared plus g dot triple prime times L squared over 2k plus g dot triple prime times L over h bar F, I guess. I'm calling it F or S. I think I've been using both. Yeah. This problem was, it's using both. It's the same value. I'll have to go back and fix the notes. But we have one H bar, right? We have one H bar going on here. Okay. Okay, other boundary condition, what? This one here. This one becomes d theta dx at x equals 0 is equal to 0. And this one becomes minus k times the derivative of theta with respect to x at x equals L is equal to h bar. Let's just call it h bar here. H bar times theta at x equals L. Okay. So we just went through and made our substitution, right? Restated our problem. You've done this before. It should be that hard despite the couple of mistakes here. Okay, but this now gives us a problem that we can separate. Right? Oh yeah, sorry. That's what it is. Okay, yep, thank you. So we have, and the problem is on the notes, S and F look really similar when they're super small. So yeah, we have F is what the initial condition, right? Thank you. Good call. Yeah. So F is the first one. S is the second. Very good. Thank you, Aiden. Okay. So we have our statement. So now we can go through and solve this using separation of variables. Okay. So here's the restated problem that we just came up with in terms of theta. So let's go through and separate this. We'll do it quickly again since we've done this before. But we're basically saying now I've got some theta, which is a function of x and a function of time. Okay, separation of variables says I'm going to separate this into some theta x, which is a function only of x, times some theta t, which is only a function of time, right? That's kind of the underlying premise. Okay, so we substitute that in and we end up with the following, which is alpha times the second derivative with respect to x of theta x times theta t, okay, is equal to the first derivative with respect to time of theta x times theta t. Okay, on the left-hand side, we can pull out theta t. On the right-hand side, we can pull out theta x, and so we're left with just rewriting this. So alpha times theta t, second derivative of theta x with respect to x is equal to theta x times the first derivative of theta t with respect to time. So unlike the previous situation where we were able to pull stuff out and kind of cancel it out, we aren't able to do that quite yet. So now we just have to divide both sides, right? So we just have to divide both sides out and we end up with our separated variables. So if we do that, we end up with this ODEs. So d squared theta x over dx squared over theta x is now equal to d theta t dt over alpha theta t. Okay. A couple things to notice, right? Now we have two second derivatives here, or one second derivative and a first derivative. But in either case, we have a situation where both of them have to equal a constant, just like before. However, they can equal the same constant, right? We don't have this sign problem like we did before. We don't have to decide whether there's a plus or minus. We just have both of them have to equal the same constant. So if we write this out, right, these both have to equal plus or minus lambda squared. So then if we move forward, let's solve the x problem first. So x is going to be d squared theta x dx squared. So now bring that over so it's minus or plus lambda squared theta x equals 0. And then the theta t problem is d theta t dt minus plus, right? They're going to have the same sign. Lambda squared alpha theta t equals 0. Okay, so to solve this problem, we still need to have a condition where we have a periodic function. We're going to be trying to get to lambdas or eigenvalues, right? So we need at least one of the functions to have a periodic solution. In order to do that, we actually are going to need both of them to have a periodic solution, right? Because they have to have the same sign. So to get the periodic solution, we have to choose positive for both of them. Okay. So we end up with this is our solution for separation of variables for the ODEs. Okay, continuing on here. So now we have to solve the Eigen problem. Okay, this is the same solution or procedure we've been doing before, but let's go through it real quick. So we have first the x problem. So d theta x dx squared plus lambda squared theta x equals 0, right? That's what we're trying to solve now. So the solution for this, for theta x, you could go to Maple, or by this time you could probably recognize that theta x is going to be c1 times sine of lambda x plus c2 times cosine of lambda x. Okay, so then taking the derivative of that, the first boundary condition here, right? This boundary condition here, taking the derivative gives us d theta x equals 0 is going to be c1 times lambda times cosine of lambda times 0 minus c2 times lambda times sine of lambda times 0. Right, and then this is just saying c1 is equal to 0. And our boundary condition says that's all equal to 0. C1 times lambda times 1 has to equal 0, so C1 has to equal 0. Okay, so then we're left with this. Theta x is equal to C2 cosine of lambda x. And this is our eigenfunction. Okay. All right, so solving the other part of it then, theta x is equal to, we just had that down there, C2 cosine of lambda times x. So now enforcing the other boundary condition at the convection boundary, we have minus k times theta dx at x equals L is equal to h bar times theta at x equals L. So we substitute in the derivative, multiply that by minus k, and then substitute in theta and multiply that by h. And we end up with k times C2 lambda sine of lambda L is equal to h bar, okay, s, h bar s times C2 cosine of lambda L. Okay. Right, C2s will cancel out here. And we're left with our Eigen condition, which is bring cosine over to the left-hand side. So then we have tangent of lambda L is equal to h bar s times L over k times lambda L, right? Or h bar over k times lambda. Right, there's our Eigen condition. Any questions on this so far? Yeah. Well, right, because the boundary condition has to be enforced for the full theta, right? So the boundary condition was still in terms of the full theta. So in this case, yeah, we can take the derivative, we pull out the theta t's will cancel just because it's, you have theta t on both sides and it can cancel out. So if you did that, then it would be the regular ODE, not the partial. Yeah. So HS was the, HF is the, yeah, this is what Eigen was saying. Back up here. So this is HF, which is the initial condition. And HS is what it becomes after you switch it off. Sorry about that confusion there. Yeah. Right, so if we pick the negative, then then the solution to that ODE is sinh and cosh, or exponentials. Those are not periodic like sine and cosine are. And so you can't get eigenvalues out of that. But our point is to get to a solution that has an eigen condition that gives us the lambdas that we can solve. Okay, so let's finish this off here. So we have now our problem that our eigen condition that we're solving. So we need to go through and find these solutions here, right? This. One thing to note, and actually this kind of escaped me the first time we talked through it and maybe led to some confusion, but the solution for this has to fall in this range, right? So the solution for this has to fall in the range where tangent is positive, right? Because it's equal to some positive constants, and where that function is positive, right? So the repeating period where you find the solution would be, say, 0 to pi over 2, and then pi to 3 pi over 2, right? So you could try to find a solution for that sort of whole range of pi, but ease is going to have an easier time finding the solution if you kind of tell it in these pi over 2 increments. So that I think I confused you the first time we talked through it, but that's kind of an easier way to find that repeating solution there. Okay, so we do that and we end up with what? The Eigen problem, or Eigen's values have to be in the range I minus 1 times pi, right, where I starts at 1, is less than lambda I times L, which is less than 2I minus 1 over 2 times pi, for I equals 1, 2, 3, and so on. Right? So that pi over 2 region rolling along is what we see here. Okay. Okay, this can be solved in ease, right? These values can be solved in ease. And then we're left with a few more steps, but I think we're out of time, so we'll leave it there for today. And I can hang around for office hours. Thanks, everyone.